question.
All right. Now, something that you would have seen in Calc 2 is parametric equations. So let's first start off by talking about the relationship between parametric equations and vectors. 11.6, let's talk about parametric equations. So right now we're just talking about, right now we're just going to talk about parametric equations of a line. So these are just other ways of doing linear functions. You can graph parametric equations in your graphing calculator. You can do it on Desmos. So if you ever want to see what these things look like, there are plenty of ways to plot them. And if you have questions about that, you can ask Professor Tar or myself. But you just need to change your mode to parametric in your calculator, and you can do parametric equations. We're going to look at some very specific things about parametric equations. Number one, this would be in 2D. So not right now, we're in the 2D plane. So this would be parametric equations that go through a point x0, y0, and they have a slope of a in the x direction and b in the y direction. Okay. Now we're used to thinking of slope as rise over run because we're looking at a function. When we're doing parametric equations, we think of each variable as having its own slope. That's a good thing though, because that allows us to relate this very easily to vectors, because those slopes give us the direction in x and the direction in y. Therefore, the vector that is parallel to this line that we're given is AB. And it is that straightforward. You know, we don't have to think about it. We know if we're given a line in parametric, AB is going to be the vector that is parallel with it. That same relationship holds. Oh, and the other thing to mention is if we're thinking about the slope of what this, the slope of this line in 2D, y with respect to x, well, we've got a rise of b and a run of a. So b over a would be the slope of the line as a function. Same thing goes in 3D. We just have another equation now for z. That's what's going to make it go up and down the z-axis. And we will do some really cool stuff later with these parametric equations. Right now, we're just kind of hitting the tip of the iceberg. You're going to get a little bit of practice with them today. And the same thing goes with the vector. Okay, just the slopes in the x, y, and z directions. So the question I got online is whether or not there should be a preference for what point, beginning or end, should be picked to fill out the parametric equation. It's going to depend on what we're doing. Right now, we're just looking at parametric equations as infinite lines in 2D and 3D. So there's no particular ending and beginning point. But that is going to be something we take into consideration as we go on, is how do we make a line that starts at one point and ends at another point, in which case we would set an interval for t. So if we wanted this to go from x0, y0, z0 to some other point, we might say t equals 0 up to whatever our ending value is. And that is going to be something that we do a little bit of as we move on with parametric equations. Because sometimes we do want them to begin and do a line segment instead of an infinite line. But right now, we're not worried about that in this section. Okay, changing gears a little bit. Linear functions. This is old stuff. In 2D, we've got a slope, change in y over change in x, right? And b gives the y-intercept, and we get the graph of a straight line. So now we need to expand this into 3D. Well, we talked about this a little bit before. A line, something that makes a line in 2D makes a plane in 3D. The only difference now is we have a slope in the x direction and a slope in the y direction. And so what happens is we look at one direction at a time. So if we keep y fixed and we want to know how z changes, z being the output, right now we're calling it f of xy. How does z change per unit change in x? Well, that's m. So what's nice about this is m is still change in output with respect to input, but just in the x direction. So what we might say, just to kind of, so m gives the change in z value with respect to a change in x holding y constant. And n is the change in z value with respect to a change in y holding x constant. Apologies for my messy writing. So for instance, we can, we have Calcplot 3D. So let me know. So one of the things, and like I said, we're not going to draw a whole lot of 3D graphs in here. It's really difficult. Planes are incredibly difficult to draw in 3D. If you ever have to draw a plane in 3D, what you do is you find where it intersects each axis and put a point there and just make a triangle. Okay, that'll kind of at least give you an idea of what the plane should look like, because it's impossible to draw a plane in 3D on axes when you're looking at a two-dimensional piece of paper. Like I said, we're not going to have to draw a whole lot of planes, so I don't want you to worry about that too much. But if you ever have to do it, if you're ever doing it for a problem, that's typically what we do, is just mark the axes intercepts and then just make a triangle between them. All right. Going back. Okay. So just a couple things I want to look at with the plane, and then we'll talk about some of those formulas that you saw in the lesson, and then we'll get to work on some problems, which is where the really interesting stuff happens. So if you imagine walking on a tilted plane, so imagine that the floor where you're at is tilted. The slope's not always the same unless we set it to be the same. But if you walk in a direction parallel to the x-axis, you'll always be walking the same slope. You walk in a direction parallel to the y-axis, you're always walking the same slope. Those are those m and n from the previous formula. So what's happening that's creating the linear function is the m and n are constant, right? Just like in 2D, the m is constant, now the m and n are constant. And x, y, and z are all to the first power. We're going to see a couple different forms of a plane. And, depending on what we're doing, one form may be more useful than another, but here's kind of a general form. If you wanted, this would be like the point normal, not point normal, excuse me, the point slope form of a line. This would be the point slope form of a plane, because all we need to do is find m and n, and then we can plug in x0, y0, and z0. Okay. Now, here's something I want to show you. This is the table for this linear function. So we know that the graph of this is a plane. It is a linear function in 3D. What kind of observations do you make about this table? What patterns do you notice? Down 3. Is there anything in the equation that would have told us that without the table? There's the -3 right there. So that tells us as x goes up 1, z goes down 3, right? As we go as y goes up 1, the z values go up 2. So that's how those slopes work. Because when we're going right across, we're holding y constant. And when we go down, we're holding x constant. Here's another cool one. What do you notice? Let me get this gobbledygook off here. What do you notice about going diagonal? You had an m of -3 and a y of +2. Add those together, you get -1. And look at the diagonals. Down 1, down 1, down 1, down 1. That's that constant rate of change of the linear function in 3D. Those are the kind of patterns we should see.
Making a lot more sense in the videos.
Okay, good. Okay. Now, something we talked about last time, we introduced the concept of the normal vector, right? A normal vector is perpendicular to something. So a normal vector to a plane is perpendicular to the plane. This is going to be a really cool and a really interesting idea, and I'm going to walk you through it. All right, suppose we have some plane. All right, this plane passes through the point x, y, z, and has a normal vector ABC. Okay, so we know that ABC is perpendicular to our plane. Well, what we're going to do is we're going to pick another point in the plane. So here's what's going on. Something other than red for once. All right, so here's our plane. We have some point P. And we're going to pick another point, let's call it Q, in our plane. Well, what I'm going to do is I'm going to make a vector from, I'm going to do from Q to Q. Let me see, I want to match my notes. Q. Yeah, let's do Q to P. Okay, well, let's think about the components. I think this is going to be the opposite of what I have on my slide, but that's okay. Let's think about the components of Q to P, right? Remember, it's ending minus beginning point. So the components will be x minus x0, y minus y0, and z minus z0. All right, so that's that. Now, what we know about that vector is it lies in the plane, right? Well, if I put in the normal vector, let's make this stand out. If I put in the normal vector, this is our normal vector here. What do I know about the relationship of n with QP? They have to be perpendicular. Boom. All right, cool. Here's another thing that we know. What do we know about the dot product between n and QP? Based on what you just told me. Louder.
It's 0.
It's 0, right? Because the dot product of two perpendicular vectors must be 0. You guys just uncovered what's called the point normal form of a plane. Like I said, I think I have it backwards. I think I wrote PQ instead of QP, so sorry about that. But what we do is we dot those two together. We know it's equal to 0, and that gives us this guy right here, which is called the point normal form of a plane. Why is this awesome? Because all we need, let me say that again, all we need to find the formula for a plane is the normal vector and a point in the plane. So this is brilliant. We're going to use this often. We don't need to derive the point normal form of a plane anymore. We can just use it. We can say, oh, I've got a normal vector and a point. Boom, there's my plane. It saves a lot of time. So And I will give you a hint. There's going to be one of the problems on the worksheet that's going to ask you to do that. And it is as easy as it sounds. So that's our point normal form of a plane. Now, let's leverage something that we talked about last time with what we just did. All right. Let's talk about a plane in 3 space. This is a fact. This is some basic geometry. Any 3 non-collinear points make a plane. Now, non-collinear means that they're not all 3 on the same line. So you have any 2 points is going to lie on the line. If you have a 3rd point not on the line, you can make a plane through those 3 points, right? So the question becomes, how can we determine the unique plane through 3 non-collinear points? Well, what are you thinking? I hear it. Yep. So let's say here's our P, Q, and R. And what we can do is we make 2 vectors. Maybe we make one here and one here, right? Now remember what we just saw in the last slide. We need a normal vector and a point that it goes through, or a point in the plane. We already have 3 points in the plane, so we're good there. How can I get a vector normal to the plane? And my hint is that we made 2 vectors. Think about what we did in the last section. The cross product. The cross product of these 2 vectors will give us a vector that we are guaranteed is perpendicular to the plane that those 2 lie in. That would be our normal vector. We can use any of those 3 points. It doesn't matter which one. And we can put together our point normal form of a plane. All right, so anytime we're given 3 points, as long as they're non-collinear, then we can do the cross product and get a vector that's perpendicular to them. That's our normal vector. And then we do our point normal form of a plane. All right. And like I said, there'll be one in the worksheet like that. That's going to be our opportunity to practice cross products. So like I said, all this stuff really starts coming together. Okay, just a couple of other formulas that are going to come up that you're going to get to use in the worksheet here in a little bit. Again, we're not memorizing formulas. You'll have a note card for those. We just need to know when to use them. We did this last time, distance between a line and a point. That was the last problem we did at the end of class. It's just a dot product. So all we do is we create a vector between the point P and some point on the line. And then we do the dot product with the normal vector as a unit vector. And boom, we've got the distance. That's the exact same thing we did at the end of class last time. We can expand that. The distance between 2 non-parallel lines in 3D. So we find a point P on one line and a point Q on the other. Okay, this is going to be a very similar idea. We don't care that those points aren't lined up. Any point that's easy to find. All we need is a vector between the 2 lines. Then we'll find a vector U parallel to one line and a vector V parallel to the other. We've talked about that before too. Remember at the very beginning, if our lines are given parametrically, we know how to find a vector parallel. Or if we know the slope of the line, we know how to find a vector parallel, right? So again, those are things that are fairly easy for us to do. Once we have those vectors U and V, well, we need a vector that's perpendicular to both of them. What do we use to find a vector that's perpendicular to given vectors? In the normal vector direction. So hopefully you guys are seeing, I know I'm going through these quick, but it's because I'm going to give you time for the worksheet, but hopefully you're seeing how really it's just the same idea applied in different situations, right? All we're doing is a vector projection in the direction of a normal vector. It's just what do we want it to be normal to? In the first case, we needed it normal to the line. Now we need it normal to 2 separate lines, which is why we need the cross product. What if we needed it for a plane? Guys, it's going to be the same idea. If we wanted the distance between a point and a plane, we got some point out in here in space, we got some plane, we'll pick any random point in the plane, make a vector between them. That'll be our PQ. And we already know the normal vector of a plane because we just saw the point normal form. So you put your plane into point normal form if it's not already, get your normal vector, and then you dot PQ with the unit vector in the direction of the normal vector. I think what's funny about these slides, even though this were 3 different problems, did you notice how the formula always looked the same? PQ dot n over magnitude of n, PQ dot n over magnitude of n. The only difference in each of these was how we found the normal vector. That's it. And that's, again, that's the part that I want you to focus on, not the formula itself. All right. Angle of intersections. Last thing we're going to talk about, and again, I just want to give you the idea behind these formulas so you kind of understand where they're coming from. So the angle between a line and a plane is pi over 2 minus the angle between the line and the normal vector of the plane. Why pi over 2? Well, remember, this is our normal vector, so it's perpendicular to the plane. So that's our pi over 2. And then, excuse me. And then if we find the angle between the normal vector and the line, call this alpha, well, we would do pi over 2 minus alpha to get theta, right? Because these two have to add up to 90 degrees for pi over 2. So that's why it's saying pi over 2 minus that. And the reason we do that is because it's easy to find the angle between these 2 lines. That's what we were doing last time. Remember, we were finding the angle between 2 vectors. Well, we would know the normal vector because it's just the normal vector of the plane, right? And that's something we're just going to get used to going back and forth from, taking the normal vector, finding a plane, taking the plane and finding its normal vector. We also know how to find a vector that is parallel to this line. So once we have those 2 vectors, then we're just doing the angle between 2 vectors, which is straight out of the dot product section. I think that was 11.4. All right. So not a brand new formula at all, just thinking about it a little differently. Lastly, the angle between 2 planes. Turns out this is going to leverage 11.42, that dot product, those 2 dot product definitions. And here's the thing. The angle between 2 planes is equal to the angle between their normal vectors. So what you would do is you take your 2 planes, find the normal vector for each, and then find the angle between the normal vectors. What's that? Yep, you got it. So I just wanted to go through those formulas because they are going to be part of problems in the worksheet for 11.6. Just to give you a little bit of an idea behind where they come from, because I know sometimes they get introduced and they're not talked about too much.